Hello, dear students. Without wasting much time, just read the title on the slide. Tangential and normal components of velocity. So, before do anything with this title, I would like to explain. Suppose you have one vector, any vector, whose name is suppose r bar, and this vector is in two-dimensional plane. That's why may I write this vector is like this: xi bar plus yj bar, right? So now this x is called as what this x is called as component of this vector r bar along this vector. And we know that I bar is a unit vector along the x-axis. Therefore, this component is called as a component of r bar along x-axis, and this is called as a component of r bar along the y-axis. So, this quantity is a component of this vector along this vector. So this is the reading skill of the vector. When we write any vector form or when we read any vector form, so what is our understanding about that vector? So it's a simple meaning. So what x and y represents in vector. So here we want to find components, okay, of velocity. That means that we have to write velocity vector in terms of something plus something. But when I will write here I bar, this will become a component along the x-axis. But I need component of velocity along the tangent. That's why here instead of I bar, we have to take unit vector along the tangent, that is nothing but t cap. And normal component means here we have to take n cap. And we know that, see, here I bar is along the x-axis, j bar is along the y-axis, and x and y both are perpendicular to each other. Here also t cap and n cap are perpendicular to each other. Only thing is, instead of along the x-axis, we are considering along the tangent and along the normal. So whatever the expression I am getting here and here, so this expression is a component of velocity along the tangent, that is called as a tangential component, and this expression, whatever I will get here, is called as a component of velocity along the normal, that is called as a normal component of the velocity. So this is the short background of this question. Now we will solve this question because it's very easy. Now here I want to find the components of velocity. So we know that velocity v bar is, as per our definition, that is dr bar by dt. The rate of change of displacement with respect to time is called as a velocity vector. That's why I have written v bar is equal to dr bar by dt, where r bar is the position vector of any point on the curve at any time t. Right? Now I have to manipulate this derivative so that I will get t cap and n cap. So can you tell me what is the t cap? T cap is a unit tangent vector, and already we have proved this, and unit tangent vector is nothing but the rate of change of r bar with respect to arc length ds. So if I want to manipulate or rewrite this derivative in terms of t cap, so I have to write this derivative by using chain rule in terms of arc length. So that's why I may write this as a dr bar by ds. Why I have taken ds? Because dr bar by ds is nothing but t cap, and t cap is a unit tangent vector. I need it for the component. That's why purposely I am writing this into uh, according to chain rule. I have to write ds here and dt here. So I have written this derivative, or otherwise in other language we can say that I split that derivative by using chain rule like this. Now this ds by dt I am putting here, ds by dt, and into this is nothing but t cap, and there is a no normal component, therefore it's a component I am taking 0 and n cap. So I am successfully written velocity vector in terms of t cap and n cap. So as per our last discussion, this is a t cap, and the coefficient of t cap is nothing but the component along the tangent. Therefore ds by dt is equal to component of v bar along the tangent, or you can say that it is a tangential component of velocity. Tangential component of v bar. And what is the normal component? The coefficient of n cap is here 0. So 0 is equal to normal component of v bar. So keep in mind, normal component of velocity is always 0, and tangential component of velocity is ds by dt. This is a very short answer of this question. Okay, fine. Now I have to write another thing, that is tangential and normal components of acceleration. So here acceleration means denoted by a bar. Okay, so now I have to write this a bar, and I have to calculate something multiply by t cap and something multiply by n cap. When I will successfully return this a bar like this, then whatever the expression in first bracket is called as a tangential component of acceleration, and whatever the expression I'll get in the second bracket, that is a multiplier of n cap, is called as a normal component of acceleration. So that's why I have to start my answer by using the definition of acceleration. We know that acceleration is nothing but derivative with respect to t of v bar. We know that this is a very fundamental definition, and this d by dt keeping as it is, and this v bar I'm writing as a ds by dt. Already in the last session we have proved this, t cap plus 0 n cap, but 0 quantity not necessary to write. So now this is a product of ds by dt and t cap. One is a scalar quantity and another is a vector, and I am taking its differentiation by using product rule. So therefore a bar is equal to derivative of first quantity, that is d2s by dt square, keeping second quantity as it is, plus keeping first quantity as it is, ds by dt, into d by dt of t cap. All right, now first term I'm keeping as it is, d2s by dt squared into t cap, and now here I have to manipulate this derivative by using which rule? Chain rule. So here ds by dt keeping as it is, and this derivative of t cap with respect to t, now I'm manipulating like this. So this is not a cross product, this is a multiplication, ordinary multiplication. So dt cap by ds into ds by dt. Fine. So in the next step, the first term again keeping as it is, d2s by dt square t cap plus this ds by dt and this ds by dt. After multiplication, I'll get square of ds by dt. So ds by dt whole square into dt cap by ds. All right. But the thing is that when you take the derivative of t cap with respect to s, what will happen? That is very important. So in the last video, we already proved that here we can mention we have keep remember this relation, this dt cap with respect to ds is nothing but curvature into n cap. Now I am putting this value here, therefore this a bar is equal to d2s by dt square t cap plus this is k into ds by dt whole square into n cap. Okay, fine. So this is a curvature. You know that the relation between curvature and radius of curvature, that's why you keep k as it is, or instead of k you may write 1 upon rho. Rho is the radius of curvature. So here I have written a bar successfully in terms of t cap and n cap, and therefore as per our previous discussion, the coefficient of t cap, this one, is the tangential component of acceleration, and coefficient of n cap, this is a normal component of acceleration. So it is denoted by, the acceleration is denoted by a, and the tangential component means at. This is nothing but d2s by dt square. Okay, and normal component is denoted by an. This is k into ds by dt whole square. This is the magic of chain rule only. You don't bother about the solution and all the things, but keep remember all the identities related to what is that dr bar dt is v bar, ds by dt is the component, and dt cap by ds is kn cap, all the things. So this is the answer. And what happened, its meaning is that acceleration may you write in terms of ij, or may you write in terms of t cap n cap, the same expression, but only components are different. If you have written a bar is equal to like this, d2x by dt square I bar plus d2y by dt square j bar, then this is called as a component of acceleration along the x-axis, and this is component of acceleration along the y-axis. The same acceleration, if you write in terms of t bar and n bar, so here you have to write d2s by dt square, already we have proved this, and here k into ds by dt whole square. So this is a component of same acceleration, but not along x-axis, it is along the tangent unit vector, and this is a component of acceleration along the unit normal vector. So keep in mind these two important things. this one. This is the tangential component of acceleration, and this is the normal component of acceleration. So how you will find the magnitude of acceleration, that is denoted by a, and this is nothing but a square root of squaring and adding of its components. If you are treating a bar like this, then you have to square and add these components, and otherwise if you are considering a bar in terms of t cap and n cap, then you have to write the tangential and normal components. Squaring, adding, and take its positive square root, you will get the scalar acceleration. That means magnitude of acceleration, right? So these are the two things only you have to consider. So now we will stop here. We will meet in the next video. Thank you.